Welcome. Today's topic is dissecting the major components of a computer. We're not going to go into the super nitty-gritty yet. We're going to start by just kind of talking at a high level about what makes up a computer, things like the CPU, the memory, input and output, things like that. But before we even go that deep, I want to talk a little bit about what makes up those components. Now we're going to keep this brief. Later I'm going to have a much more detailed explanation of transistors and how they work. For now, we just want to understand that a transistor is kind of the most fundamentally discrete part of the computer components that we're going to discuss. A transistor is an electronically controlled switch. Now, this is a little bit different from the switch on your wall, right? Your finger or muscle action controls the switch on your wall, but the result is the same. When you turn on the switch on your wall, the light comes on in your room, hypothetically. A transistor is very much like that. A computer has some electric power applied to a supply line, just like your light has some electric power that's ready and waiting to be supplied to the light before you turn the switch on. The computer uses a control wire. This might be set by an input that you provide. If you had a Boolean value, for example, like a true or a false, a true might symbolize that this wire gets voltage applied. When this control wire has voltage applied, that means that the voltage in the supply can flow through the transistor and out the other side, which we can then measure and say that this transistor is in fact showing a value of 1. It is on. So this is very much like a switch on your wall. You turn on the switch on the wall, the light in your room comes on, and you can see that light. You can read it and say, okay, the light is on. So that is the most fundamental component of the computer that we're going to discuss. And this is actually what makes up the CPU, and it also is involved in memory and most other components of the computer. A transistor is made up of silicon. Now, silicon is what's known as a semiconductor, and you've probably heard these terms before. A semiconductor just means that it has electrical conductivity, but it's not the greatest. It's not a highly conductive metal like copper. It's not something you would put in a wire to move electricity from one place to another. But it's not an insulator either. It's not something that prevents electricity completely from moving from one place to another. The interesting thing about silicon is that it can be doped, or you can add other chemicals that allow silicon to change its conductive properties. So when we apply voltage on this control wire, it can become more conductive and allow the electricity to flow through. But when we take voltage away, we can prevent the electricity from flowing through this transistor or electronic switch and hold it in one spot. So it's this unique property that allows us to use silicon as the material to create a transistor, which allows us to build electronic computers. Electronic computers are important because they are very fast in how quickly these switches can turn on and off. And that is why we can have computers that do billions of things a second. If we had to have a mechanical process manipulate this switch like a relay, things are much slower. So now that we understand at a basic level what a transistor is, it's just basically an electronic switch, let's look at how we use that to build what's known as an integrated circuit. So an integrated circuit is basically just a combination of hundreds, thousands, millions, billions of transistors into a single chip. There's been many manufacturing processes that have happened as this has grown and throughout the years. If you go back far enough, before we had transistors at all, there were things like vacuum tubes. A vacuum tube was not very fast. A vacuum tube in reflection of what we can do with a transistor today was excruciatingly slow, but it did perform the function that we needed to do, which was to store a 1 or a 0. A transistor now is much faster because it's electronically switched. There's no mechanical part, there's no vacuum, and in fact, there's nothing to burn out. So one of the early problems with vacuum tubes is that they had a lifespan of how many times they would actually work. And it was very common for computers with hundreds, thousands, or many thousands of these vacuum tubes to run into problems because the vacuum tubes would fail in the middle of running a calculation. A transistor is much more resilient and hardy and lasts a lot longer time. In the 1970s, we started building transistors into what are known as integrated circuits, bringing more and more transistors into one piece of silicon. And this kept going. We went from a regular integrated circuit to a very large-scale integrated circuit, and most recently, manufacturing processes have reached what's called an ultra-large-scale integrated circuit. This just means that we can keep getting more and more transistors into a relatively small amount of silicon, and as we do, the possibilities of what we can do with those transistors to make our chips better, faster, improve, and they improve a lot. This is actually the idea behind Moore's Law, which we also discussed in this other video. If you haven't checked that out, please do. So what are the 5 components that we're going to think of at a high level that make up a computer system? Well, they're really at this point things that the computer must perform. It must be able to gather input. We must be able to give the computer information that it can work with. It also has to be able to provide us output. It needs to be able to tell us what the results of our calculation was. It has to have memory. It has to have a way to store information that it's working with, at least at the moment in time that it's working with it, but more often than not, it also involves storing things long term as well. We also have to have a way for this information to flow through the computer. We're going to refer to that as the data path, or ALU, depending on which part it's flowing through and what's happening. And lastly, we need control. We need a way to tell the information which way to flow. You can think of this for a moment as what we were just discussing with transistors. We need a way to kind of turn the transistor on and off and allow electricity to flow. And that is the same when you kind of zoom out and think of the computer as a whole. We need a way to control this computer, whether it's through machine instructions or things like that. We need a way to tell it what to do. Should it add? Should it store information? What is the next step in the process? We can visualize this a little bit like this. So if you imagine here that we have our input, so we have information coming into the computer, that information is going to first go to the computer's memory, where we can hold on to it, use it, change it, manipulate it, add to it, anything we need to do. From memory, we can retrieve things that we're working with and send them down the data path using control to say, go get this thing from memory, put it in the data path. And as part of the data path, you have an ALU that performs computation, which manipulates the data. So if you're adding 2 numbers, say you're adding 2 plus 2, you had 2 2's come in and you have a 4 come out, right? That 4 now can be stored back in memory and provided as output to the user. There's some other pieces here that I'm not going to dive in right now. The compiler up here represents the idea that we can write high-level computer programs that get compiled down to what are called raw machine instructions, which manipulate this control here and tell the computer how to react and how to act with the information that I'm getting from memory and sending down the data path. So let's see how these kind of conceptual 5 ideas actually relate to real computer components. So the hardware, when we refer to the hardware and the software, we know that the hardware forms the tangible part of the system. This is the physical machine that we can touch and visually see. We have input and output devices that are connected to it. So our keyboard, our mouse, these are input devices. Our microphone that I'm using right now to record this video is an input device. Output devices are screens, things like that. Speakers are output devices. We also need some kind of storage devices. So this is going to include memory, it's going to include RAM, and it could also include long-term storage as well. We're also going to have the CPU, or central processing unit. Nowadays, we think of a CPU more as a core because normally computers have multiple core or multiple CPU systems. We'll talk more about that later. But our CPU is made up of an ALU, which is that Arithmetic Logic Unit. This is where we actually can do the data manipulation when we do things like add, for example, or we perform some logical operation. Is something true or false, or do we need to do something called a bit shift? Things like that can all happen in the ALU. The control unit is the piece that we use to control the flow of information through the data path. So the data path has many components like buses and the ALU, but the control unit is where we again direct the flow of the information through the computer, through the ALU, in and out of memory. The last thing here about the CPU we need to talk about is the interface unit. The CPU is the brain of the computer. It's the heart of the computer. It's where, most of the important stuff, quote unquote, is going on. We need to interface the CPU with the rest of the computer. So that's the job of the interface unit. It allows the CPU to talk to things like memory, to talk to I/O or input and output devices. It allows information to flow in and out of the CPU. We also have memory. Now, memory can come in many forms, but we're going to concentrate on memory as you think of RAM or random access memory, but the actual memory that you are currently using in your program to work on an active program and the data that goes with it. So let's look a little bit deeper at the CPU and its components. So we mentioned that ALU, right? That's part of the data path, and we know that it provides the arithmetic and the logic unit. So arithmetic is usually part of an adder. So a adder allows us to literally add two numbers, but as we'll learn later, if we use signed numbers, we can also use an adder to subtract. So for example, if I add the numbers 4 and -2, I am effectively subtracting 2 from 4, even though I said that as let me add a 4 and a -2, right? So you can actually perform all of addition, subtraction, multiplication, and division with an adder. Now that's not to say that CPUs don't have more complex circuitry that can speed up some of those other operations, but all that's actually required is an adder. We also have a control unit. So the control unit is, again, what we're going to use to decide how we're going to process our data by using those instructions. So let's say that we do want to subtract in our program. Our program says, I do want to subtract, a -2 or a 2, let's just say, from a 4. The control unit takes that instruction and sends the correct signals to the adder so that the ALU does in fact do the subtraction. It's the control unit's job to kind of be the conductor of the orchestra. It is the one that tells which wires to conduct information or electricity, which is conducting information, at any given moment to affect the result that we want. So when we talk about a computer and we break down this idea of an instruction set architecture, and we say that what we're marrying here is the hardware, the physical components, like how many registers does the CPU have, and the instructions, which are the things we can tell it to do, the control unit is where that all comes together. The control unit is where we say, if I give you an instruction of 1010, that means that I want you to do an addition. So the control unit takes that 1010 instruction and turns on 2 out of 4 wires that are wired to the ALU. And when those 2 wires are wired on hot, that means that the ALU will do addition. Perhaps if we gave it 1011, that would mean that the ALU would do subtraction. It is the control unit's job to take that instruction and convert it to physical action of the hardware by actually changing the control wires of the hardware so that those things happen. Lastly, we have the interface unit within the CPU. The interface unit moves the instructions and data between the CPU and other hardware components. Now, this includes a lot of different components, and we're going to talk much more in detail about that later. However, what I want to talk about now is where this information is moved over. So we refer to the groups of wires that move information from component to component as a bus. Now, buses exist in many places. They can exist within the CPU. They can also exist between the CPU and other components. A bus is simply a bundle of wires that carry electrical signals. They can provide power, they can provide control, they can provide different functions, but all they are wires. You can think of them just like the wires in your wall that conduct electricity, that bring information from one place to another. They come in different styles, so there's serial buses and parallel buses, and we're going to talk more about those later when we get into I/O. But for now, just know that a bus is a bundle of wires, and it is the piece that we need to move information from one place to another. You can also think of it as the highway, right? For your car to get to work, you have to, go down a few roads, and maybe you go down an interstate, and that you can think of as like a bigger bus, right? There's more lanes. Maybe you live in New Jersey or California and you have, 5 or 6 lanes wide on your interstate. Well, you have a big bus, right? You can carry lots of signals. Or maybe you take a country road and there's only 1 lane in each direction, right? So that is a much smaller bus. But at the heart of what we're discussing here, a bus is just a way to move information from one place to another. All right, so now that we've looked at a high level at the CPU, let's look at its counterpart, which it absolutely needs to function, known as memory. So memory, remember, can come in many flavors, but I'm going to concentrate right now on what we think of as RAM, or random access memory. The memory that we're using right now that has the instructions of our program and the data that that program is using. This is the memory that you think of as, if I accidentally pull the power from the computer and I haven't saved my document, I've lost it because this memory is what's called volatile, right? It might go away if you take power away, as opposed to longer term storage or non-volatile storage like your hard drive, where you store information like a file that contains, say, your resume that you want to open at a different date. When you're actively editing your resume, you're using primary storage or RAM. When you store your resume for a future time, you're using secondary storage, or maybe your hard drive is another way to think of that. So what is memory? So memory, just like the CPU, is made up of transistors. Now, there's different memory technologies, and some use capacitors, and I'm not going to get into the differences there. That's not super important. What is important is that it's the same fundamental switch. It's either storing a 0 or a 1. Now, that means that everything that we put into memory has to be fundamentally broken down and stored as 0s and 1s. That includes your resume, it includes the videos of your cat doing a little dance, it includes sound files and music files and all kinds of things. So all of these types of data have to be stored as a 0 or 1. Now, once we understand that we get it down to a 0 or 1, we're basically going to put this information into memory, and then we're going to use the control part of the CPU to decide which areas of memory we're going to access and bring through the data path and into the ALU to change in some way, and then store perhaps results back into memory. Memory, it's important to note, holds both the program's instructions, meaning from our earlier example before, I want to add, and the data that the program is working with. So in our earlier example, we added the numbers 4 and -2. So in this case, we have one instruction add, and we have 2 points of data, 4 and -2. All 3 of these things will be stored in memory. This is what's known as the stored program concept. It simply means that the program is stored in memory along with the data, and there's no necessary structure to where in memory you store instructions versus data. There's one little caveat to this that happens in real machines in level 1 cache, and we're going to talk about that later, where instructions and data are actually separated out. But that is an organizational decision that is made to speed things up at that level. It's also the difference, if you watch the video on the difference between the von Neumann and the Harvard architecture, that means that our current machines are in fact a modified Harvard architecture and not a straight von Neumann. What I want to kind of stress right now is that both of these things, instructions and data, are both in memory, and for now we can think about them as just occupying any old space in memory. There's not set memory for instructions and set memory for data. The last thing I want to just talk a little bit about here is primary storage and secondary storage. So when I say primary storage, we're talking about information that is directly accessible by the CPU. So you're talking about information in RAM. You're talking about those instructions and data that you're actively using. Secondary storage is information that is not directly accessible by the CPU. So you can think about this as your hard drive. When you save a file to your hard drive, it's actually stored there using a file table that's managed by an operating system. It is not actually directly accessible to the CPU. When you want to open that file in your program, you go to a file menu and you find the file and you click open. At that moment, that file is then brought across and put in primary storage as data so that your program can work with it. Memory has two fundamental types of how we actually construct the memory itself. I mentioned earlier that some memory is made out of capacitors. So that is actually referred to as DRAM or dynamic RAM. It's much more common. It's a little bit or a lot cheaper to make. It requires less electrical power. And it's important to note that even though both of these are generally volatile, this one is generally always volatile. And I'll get to that difference in SRAM later. But essentially, this is if you've ever built a computer or seen computer components and you look at a RAM module, you are looking at dynamic RAM or DRAM. It usually has a lot more storage space, so you can get, today you can get RAM modules easily in 4 gigabit, 8 gigabit, even larger sizes, for a single module and then combine those. But SRAM is more expensive and is made out of transistors and silicon, so it is not the same fundamental technology. SRAM is generally used inside the processor itself, so we're going to talk more about registers as we go through these videos. Registers are discrete places where you can store little bits of information that you're currently using in the data path. And cache. Cache is a type of memory that is etched into the silicon of the CPU or nearby it, between the CPU and memory, and it is much faster, but it is usually much smaller than what you have in DRAM. So to put this in perspective, you may have 8 or 16 or 32 gigabytes of DRAM in your computer, and you may have 4 or 8 megabytes of SRAM or cache. It's a much smaller size than you have in DRAM. However, it is very, very fast in comparison to DRAM. We mentioned the term volatile before a few times, and we said that both DRAM and most forms of SRAM are volatile. So volatile, remember, means that when we take power away, whatever's in memory is lost. It is not kept. This is different from, say, what you're used to for your SSD or hard drive, where information is kept. Non-volatile memory is the term we use to describe things that don't disappear. So your hard drive is hopefully non-volatile memory. If it was volatile, you'd be very sad. There are other types of non-volatile memory as well. A ROM, or read-only memory, is an area that we hold a little bit of software that's expected to not really change over the lifespan of the system. The good example of this is the firmware used to boot the system. This was normally referred to as the BIOS. And it is the little bit of code that is run when you first turn on your computer system. It essentially knows where to find the bootloader and find the right hard drive and all that, and then the rest of your software can be loaded into memory and take control. Another version of this is called flash memory. Flash memory is essentially a version of SRAM that has a way to store the charge in the transistor so that it is not lost when you take power away. This is a relatively inexpensive, non-volatile secondary storage mechanism, and this is how our SSD drives work that have become so prolific over the last 10 years. It is very useful for storing things long term, and it is faster to store things this way than it was on the traditional spinning magnetic hard drive. We're going to dive much deeper into cache in later videos, but I want to give a quick introduction to it here because it's an important concept in how we keep our CPU, which is very hungry for information, running at billions of cycles per second, well fed with information that it can work with instructions and data. So cache is a small, fast part of memory in SRAM. Remember, that's that transistor-based in silicon faster memory technology that acts as a buffer to the slower DRAM. So remember, we said our DRAM may be, I'm going to just use one example here. Let's say we have a pretty well optioned computer and it has 32 gigabytes of RAM. That is our DRAM, right? So that is our section over here. Now let's say that our CPU has 8 megabits of total of cache memory, which is also pretty good. And that is this middle part here. This cache memory is in between the CPU and memory. When the CPU asks for a particular location in memory to be retrieved, that request goes through the cache memory. The cache memory actually looks first to see, do I have this thing in memory right now? If I do, I'm just going to return it. If I don't, then I'm going to go to RAM, get the thing that I need, and return it. Now, you might think, well, doesn't this slow down the process a little bit? And the answer is, for what's called a cache miss, or a time when something is not in cache memory, the answer is yes, it does slow it down just a little bit. But if it's a cache hit, or you didn't have to go to memory because the thing you needed was in cache, then things are sped up quite a bit. So we'll dig into the details later, but the gains that cache gives us far exceed any downfalls that it slows down getting information from memory. In fact, there are many levels of cache that are hierarchical within themselves and speed things up even more within cache itself. Level 1, level 2, level 3, etc. We'll dig more into that in the future. In fact, there's this whole hierarchy of memory. So this is usually represented as a triangle where you have, going up the memory here, you have higher speeds. So at the top, you're looking at the fastest memory, and at the bottom, you're looking at the slowest memory. But you also have the opposite with the capacity. So at the top, you have the smallest memory, and at the bottom, you have the largest amount of memory available to you. Now, cost also follows this triangle. When you look at cost per megabit, gigabit, kilobit, whatever the measurement is, when you look at the bottom of the triangle, you have the lowest cost, and when you look at the top of the triangle, you have the highest cost. So when you look here at the top, you're looking at the ALU, you're looking at the register, then right below that, you're looking at cache, because remember, at this point, you're still in SRAM, which is transistor-based and fast. Then you might have some levels of cache that are off the CPU core. Those might be a little bit slower than the ones that are on the CPU core. Then you might have your main memory, right? So this is your RAM. This is that DRAM that is going to, hold gigabits of information that you're working with. Now, this is your primary storage, right? This is all the things that the CPU can address directly, meaning if I give the CPU an address and say, load a piece of information from memory address, 32564, then that means that the memory can see that address. 32564 can be requested from cache, and if cache doesn't have it, it'll go through the levels of cache until it gets to DRAM, and then RAM will say, okay, I have that thing, here's 32564, and it will send it back up the chain, and it will actually, by the way, insert that into cache so that next time you look for it, it might have it, and it will make it all the way back up to the ALU. Anything down here is secondary storage. This is information that the CPU cannot directly access. So when I mentioned before that your operating system keeps track of files stored on disk, those things are accessed in this manner. And when you load that file, you take the file off of your flash or your hard drive storage and put it into your main memory, at which point the CPU can then directly access it. So these things are much slower than anything up here, even if the flash storage is made out of SSD and is technically transistor based. It is still many times slower than using RAM because it is secondary storage and it has to be brought from the secondary storage into primary storage before you can actually use it. Now we can go even beyond that, and we can think about things like tape, what used to be tape backups back in the day, but now we think of as cloud storage, right? So you can use different forms of cloud storage to store information that's not even on your computer at all. So now you have to wait for a network connection to bring that information to you, and depending on the speed of your network connection, that may take different amounts of time.